calculus. For today, I will discuss with you the first three hyperbolic functions. The hyperbolic cosine, hyperbolic sine, and the hyperbolic tangent. These hyperbolic functions are defined in terms of the exponential function e to the x. And for each of the first three hyperbolic functions, we will find the range, the domain first, the range, and we will sketch the graph of each of the first three hyperbolic functions. And we will start off with some identities involving hyperbolic cosine, hyperbolic sine, and hyperbolic tangent. We start with the hyperbolic cosine. In terms of the exponential function e to the x, the hyperbolic cosine denoted by cos h of x, hyperbolic cosine of x, is defined as e to the x plus e to the minus x all over 2. And by this definition of hyperbolic cosine, we say that the domain of the hyperbolic cosine is the set of real numbers. For any real number that you substitute for x in this equation that defines hyperbolic cosine, there is a corresponding value of the hyperbolic cosine function. So the set of real numbers is the domain of the hyperbolic cosine. Now we sketch the graph of the hyperbolic cosine in the Cartesian plane or in the xy plane. And for each value of x, we calculate the value of y given by the hyperbolic cosine of x defined by e to the x plus e to the minus x all over 2. We assigned an initial value for x and we assign 0 for x. When x is 0, the value of y is given by the hyperbolic cosine of 0. When x is 0, the value of y is equal to hyperbolic cosine of 0. And by definition of hyperbolic cosine of x, hyperbolic cosine of 0 is equal to e to the 0 when x is 0, e to the 0 plus e to the minus 0 all over 2. Now, e to the 0 is 1. And e to the minus 0 is the same as 1 over e to the 0. By property of exponent, e to the minus 0 is 1 over e to the 0. But e to the power 0 is 1 and 1 over 1 is 1. And 1 plus 1 is 2. Divide by 2 is 1. Hence, when x is 0, the value of the hyperbolic cosine of x when x is 0 is 1. And when we plot this point, 0, 1, x is 0, y is 1, it means that the graph of the hyperbolic cosine of x will pass through the y-axis at the point 0, 1, or at y equals 1 on the y-axis. Now we assign values of x that are positive. We now assign values of x that are greater than 0 and are increasing and approaching positive infinity. That means we will assign values of x that are increasing to positive, that are becoming large and large up to positive infinity. And let's investigate what will happen to the value of y if the value of x approaches positive infinity. Again, we investigate what will happen to the values of y if the values of x approaches positive infinity, that is, the values of x are increasing. And the value of y will approach to what number if the value of x approaches positive infinity. So we get the limit of the hyperbolic cosine of x as x approaches positive infinity. But the hyperbolic cosine of x is defined as e to the x plus e to the minus x, or all over 2. And we get the limit of this function, and we apply properties of limits. And here we have 2, a constant in the denominator, so we can take 1/2 out of the limit, and we write this as 1/2 times the limit of e to the x plus e to the minus x. Again, we apply another property of limit, that is the limit of a sum is equal to the sum of the limits. Hence, this 1/2 times the limit of e to the x plus e to the minus x is equal to 1/2 times quantity limit of e to the x plus limit of e to the minus x. And we evaluate each limit as x approaches positive infinity. Continuing from here, 1/2 times the limit of quantity e to the x plus e to the minus x is now equal to 1/2 times quantity limit of e to the x plus limit of e to the minus x. But e to the minus x by property of exponent again is equal to 1 over e to the x. Thus, the limit of e to the minus x as x approaches positive infinity is equal to the limit of 1 over e to the x as x approaches positive infinity. Now, the limit of e to the x as x approaches infinity is equal to infinity. Because as x increases, the value of e to the x increases. That is, as x becomes large larger and larger, the value of e to the x also becomes larger and larger. But the limit of 1 over e to the x as x approaches infinity is 0. Because if x approaches infinity, e to the power x becomes very, very large. And if you divide 1 by a very, very large positive real number, the value will approach 0. The value of 1 e to the x will approach 0 as x approaches infinity. Because again, as x approaches infinity, e to the power x approaches a very, very large number, and 1 over e to the x will approach 0 as x approaches infinity. Thus, the limit of the first term is positive infinity, plus the limit of the second term is 0. And a very large number plus 0 is equal to the very large number, represented by positive infinity, and multiply that by 1/2, it becomes even larger, and it's still a positive, a very large real number denoted by positive infinity. Thus, we have shown that if x approaches positive infinity as x increases, the value of y also increases. Graphically, that means that the graph of the hyperbolic cosine, after this point, if x approaches if x approaches positive infinity, if x becomes larger and larger, the value of y also becomes larger and larger. That means the graph will, from a point after x equals 0, the graph of the hyperbolic cosine will continue to increase, and it would look like this. Now, we investigate what happens to the graph of the hyperbolic cosine of x, or what happens to the value of the hyperbolic cosine of x if x now becomes smaller and smaller and is approaching negative infinity. We now investigate what will happen to the value of the hyperbolic cosine of x, or to what number will the hyperbolic cosine of x approach to if x approaches negative infinity. That is, if x becomes smaller and smaller, what will happen to the value of the hyperbolic cosine of x given by y, or y will approach what number if x approaches negative infinity. Hence, we take the limit of the hyperbolic cosine of x as x approaches negative infinity. But the hyperbolic cosine of x, as we defined earlier, is given by e to the x plus e to the minus x all over 2. And we again apply properties of limits. We take 1/2 out of the limit, and we apply the property for the limit of a sum, which is equal to the sum of the limits. Hence, this limit is equal to 1/2 times the limit of e to the x plus the limit of e to the minus x as x approaches negative infinity. Now we examine each limit in this sum. The limit of e to the x as x approaches negative infinity is 0. Because if x here, the values of x here are negative, and those values of x are getting smaller and smaller through negative values of x. So if the value of x is negative, you have e to a negative number, and that is equal to 1 over e to that number, to that value of x. If x is negative, the exponent of e is negative, and we apply a property of exponent. That means e to the negative is equal to 1 over e to the negative e to that number. And if we evaluate that 1 over e to the x, for x approaches negative infinity, the result would be 0. So the first term approaches 0. And here, the limit of e to the minus x as x approaches negative infinity is positive infinity, because we have a negative coefficient here of x, and x is negative. If x is negative times negative, then the exponent of e would be positive. And e raised to a very, very large real number is a very, very large real number denoted by positive infinity. Thus, the limit of e to the minus x as x approaches negative infinity is positive infinity. But infinity, a very large number, plus 0 is a very large number. Infinity, positive infinity, multiplied by 1/2, the product becomes even larger, but it's still a very large number denoted by positive infinity. Thus, 1/2 times quantity 0 plus positive infinity is positive infinity. Now, what does this result tells us about the graph of the hyperbolic cosine? If the values of x approaches negative infinity after 0, if you assign values of x that are getting smaller and smaller approaching negative infinity, the value of the hyperbolic cosine of x, which we denote by y, the value of y will approach positive infinity. The value of y will become larger and larger. If x becomes smaller and smaller, the value of y becomes larger and larger. So it tells us that if x approaches negative infinity, the value of y approaches negative infinity. Graphically, geometrically, that means that the graph of the hyperbolic cosine will also continue to increase, will be increasing after 0 if values of x that are negative approaching negative infinity are assigned to x. And the value of the hyperbolic cosine will approach positive infinity, and the graph for those values of x that are negative will look like this. We have shown that as the values of x approaches positive infinity, the values of y approach positive infinity. We have also shown that as the values of x approach negative infinity, the value of y approach positive infinity. And you can see from this graph that the range is from positive 1, including positive 1, up to positive infinity. Using interval notation, the range of the hyperbolic cosine is the half open interval from 1 to positive infinity, including 1. That is why we use a bracket at 1. Now, the graph of the hyperbolic cosine is symmetric with respect to the vertical axis or the y-axis. That means the y-axis equally divides the graph of the hyperbolic cosine into two parts. The part to the left of the y-axis and the part to the right of the y-axis. And we label the graph with its function y equals hyperbolic cosine of x. And before we define the hyperbolic sine of x, we can actually show that the graph of the hyperbolic cosine is symmetric with respect to y, and we do that algebraically. First, we define vertical symmetry or symmetry with respect to the y-axis, given the function y equals f of x, such as the hyperbolic cosine of x. For y equals f of x, if f of minus x equals f of x, then the graph of y equals f of x is symmetric with respect to the y-axis. In our discussion, our f of x is hyperbolic cosine of x. And from here, f of x equals hyperbolic cosine of x, we compute f of minus x. F of minus x is obtained by replacing x with minus x in f of x equals cosine hyperbolic cosine of x, which is defined in terms of the exponential functions e to the x and e to the minus x. Hyperbolic cosine of x equals e to the x plus e to the minus x all over 2. The value of f of minus x is the hyperbolic cosine of minus x, defined by the hyperbolic cosine is defined by this. So in this equation, we replace x with minus x. Replace every x in this equation. Here, replace x with minus x. We already have hyperbolic cosine of minus x. And the value of this is obtained by replacing every x from this expression. So the hyperbolic cosine of minus x is equal to e to the minus x plus e raised to negative. Replace x with minus x all over 2. And we simplify each term. We have e to the minus x remains the same. Negative times negative x is positive x. So the second term is e to the positive x all over 2. But e to the minus x plus e to the x all over 2 is exactly the hyperbolic cosine of x, except that the sum in the numerator is interchange, but addition is commutative, which means that the sum e to the x plus e to the minus x is equal to the sum e to the minus x plus e to the positive x. Thus, this is equal to the hyperbolic cosine of x, which is equal to f of x. And we have shown that f of minus x is equal to f of x. Therefore, we conclude that the hyperbolic cosine of x is symmetric with respect to the y-axis. That means again that the y-axis divides exactly the graph of the hyperbolic cosine of x into two parts, into two equal parts. The part to the left of the y-axis and the part to the right of the y-axis. Now, to summarize, the hyperbolic cosine of x is defined in terms of the exponential functions e to the x and e to the minus x. In particular, hyperbolic cosine of x is equal to e to the x plus e to the minus x all over 2. And the hyperbolic cosine is defined for every real number. That means the domain of the hyperbolic cosine of x is the set of all real numbers. And we have shown that the range when we sketch the graph of the hyperbolic cosine of x, the range of the hyperbolic cosine of x is the open interval from positive 1 to positive infinity. And we have also shown that one of the properties of the graph of the hyperbolic cosine is symmetry. It is the graph of the hyperbolic cosine is symmetric with respect to the y-axis. We now define hyperbolic sine of x. The hyperbolic sine of x is also defined in terms of the exponential functions e to the x and e to the minus x. In particular, hyperbolic sine of x is equal to e to the x minus e to the minus x all over 2. And you may notice that the only difference between the hyperbolic cosine of x and the hyperbolic sine of x is the sign between e to the x and e to the minus x. For hyperbolic cosine of x, the sign between e to the x and e to the minus x is positive. But for the hyperbolic sine of x, the sign between e to the x and e to the minus x is negative. And because the exponential function is defined for every real number, the domain of the hyperbolic sine is the same as the domain of the hyperbolic cosine. The domain of the hyperbolic sine is the set of all real numbers, which means that the hyperbolic sine is defined for every real number that you would substitute. You may want to substitute for x. Again, we sketch the graph of the hyperbolic sine in the xy plane or Cartesian plane. When we graph the hyperbolic cosine, we start with the initial value of x equals 0. When x equals 0, we find the value of the hyperbolic sine of 0. And here our function y equals f of x is the function y equals hyperbolic sine of x. If we want to sketch the graph of the hyperbolic sine in the xy plane, we represent the value of the hyperbolic sine of x at each value of x by y. So we let y equals hyperbolic sine of x, and the value of x can be any real number on the horizontal axis or the x-axis or the real line. And we start with x equals 0. If x equals 0, y equals hyperbolic sine of 0. And the hyperbolic sine of 0 is obtained by the definition of the hyperbolic sine of x by replacing x with 0. Hyperbolic sine of 0 equals e to the power 0 minus e to the negative 0 all over 2. Again, by property of exponent, any real number raised to power 0, any non-zero real number raised to power 0 is 1. And e is not equal to 0 because e is an irrational real number with a value that is non-terminating, non-repeating decimal number. So e to the power 0 is 1. Minus, and by property of exponent, e raised to negative 0 is equal to 1 over e to the power 0. All over 2. Now again, e raised to 0 is 1, and 1 divided by 1 is 1. Hence, denominator simplifies to 1 minus 1 all over 2. And 1 minus 1 is 0. 0 divided by 2 is 0. And what does this mean? If x is 0, the value of the hyperbolic sine of x, or the hyperbolic sine of 0, or the value of y is 0. So we have the point 0, 0, which is the origin. That means that the graph of the hyperbolic sine will pass through the origin, or the origin is a point on the graph of the hyperbolic sine of x. Now we investigate, as we did in hyperbolic cosine, what happens to the value of the hyperbolic sine of x if x approaches positive infinity, or if x approaches a very, very large number. Also, we investigate what happens to the value of the hyperbolic sine of x if we assign values of x that are decreasing, approaching negative infinity. We now find to what number the value of the hyperbolic sine of x will approach to if we let x to approach positive infinity. That is, if we let x to become bigger and bigger, larger and larger, then y equals the hyperbolic sine of x will approach what number? And that number is what we call the limit of the hyperbolic sine of x. Hence, y approaches a number which is equal to the limit of the hyperbolic sine of x as x approaches positive infinity. But the hyperbolic sine of x is defined as e to the x minus e to the minus x all over 2. So we replace hyperbolic sine of x with this value in this limit. Now, the limit of the hyperbolic sine of x as x approaches positive infinity is now equal to limit of e to the x minus e to the minus x all over 2. Because hyperbolic sine of x is defined as e to the x minus e to the minus x all over 2. And we apply properties of limits to evaluate this limit. First, we take out one half, a constant, out of the limit, and we evaluate the limit of this difference by getting the difference of the limits of each of these two terms. Hence, y approaches This limit is now equal to 1/2. Multiply by the limit of e to the x as x approaches positive infinity. Minus the limit of e to the minus x as x approaches positive infinity. But if x becomes very, very large, then e to the power x will also become very, very large. That is, if x approaches infinity, e to the power x will also approach positive infinity. Thus, the limit of e to the x as x approaches positive infinity is positive infinity. And we apply property, one of the properties of exponent to e to the minus x to remove the negative exponent. So e to the minus x is equal to 1 over e to the power x. And this becomes minus the limit of 1 over e to the x as x approaches infinity. Now, if x approaches infinity, e to the power x will approach a very, very large positive real number, or will approach infinity. If x approaches positive infinity, e to the x will approach infinity. And 1 over infinity, or a very, very large real number, is 0. Thus, 1e to the power x will approach 0 if x approaches positive infinity. And this now becomes 1/2 times quantity infinity minus 0. But infinity minus 0 is still a very large real number. Multiplied by 1/2, it becomes even larger, a positive infinity. Hence, 1/2 times quantity positive infinity minus 0 is positive infinity. Now, this tells us that as we let x approach, if we assign values of x that are increasing, approaching positive infinity, the value of y will also approach, positive infinity. As from the point after the origin, if x approaches positive infinity, the value of y will approach positive infinity. That means geometrically that the graph of the hyperbolic sine of x is increasing from the point after the origin. For values of x that are increasing, the value of y will also be increasing. And the graph for those values of x will look like this. As x increases, the value of y also increases, approaching positive infinity. As x approaches positive infinity, the value of y approaches positive infinity. Now we investigate to what happens to the value of y, or the hyperbolic sine of x, if we now let x to approach negative infinity, or what happens to the hyperbolic sine of x if we assign values of x that are decreasing. To continue with sketching the graph of the hyperbolic sine of x, we now investigate what happens to the hyperbolic sine of x if x approaches negative infinity. What will happen to the values of the hyperbolic sine of x if we assign values of x that are decreasing, approaching negative infinity? To what number will the value of y equal to the hyperbolic sine of x approach to? And that number is what we call the limit of the hyperbolic sine of x. and the values of y will approach that limit or that number. So we take the limit of the hyperbolic sine of x as x approaches negative infinity. We are interested in what number the value of y will approach to, and that number is the limit of the hyperbolic sine of x as x approaches negative infinity. And we replace hyperbolic sine of x with e to the x minus e to the minus x all over 2. And again, to evaluate this limit, we apply two properties of limits. The limit of a constant and a function is equal to the constant times the limit of the function. And applying that property, it means that we can take out 1/2 out of the limit. And to evaluate the limit of the difference, we get the difference of the limits of e to the x and e to the minus x. Thus, the limit of this expression is equal to 1/2 times the limit times quantity, limit of e to the x minus limit of e to the minus x. Now we evaluate each of these limits. We start with limit of e to the x as x approaches negative infinity. If x here is a negative infinity, a very, very small real number, we apply a property of exponent. So we have e raised to a negative infinity, a very large real number, would be equal to 1 over e raised to the positive, very, very large real number. And the value of 1 over the positive, very, very large real number is 0. So the limit of e to the x, if x approaches negative infinity, is 0. Minus, and we apply property of exponent to remove the negative exponent here, and we write limit of 1 over e to the x as x approaches negative infinity. Now, if we have removed the negative exponent here by property of exponent, e to the minus x is equal to 1 over e to the x. But x approaches negative infinity, hence the exponent of e here is negative. And if you remove again that negative exponent, you have to bring it up in the numerator, and the exponent of e would be positive. And if that exponent of e is a positive, a very, very large real number, then e to that very, very large real number is equal to positive infinity. Thus, the limit of 1 over e to the x as x approaches negative infinity is positive infinity. And this simplifies to 1/2 times quantity 0 minus infinity. And 0 minus a very, very small real number is still a negative, very, very small real number. And multiply by 1/2, positive 1/2, multiplied by a very, very small real number would still be negative, and would still be a very, very small negative real number. Hence, 1/2 times 0 minus negative infinity is negative infinity. Hence, we have shown that if we let the values of x to decrease, approaching negative infinity, the value of y will approach negative infinity. If the values of x will approach negative infinity, the value of y will approach negative infinity. That is for value of x after x equals 0. And geometrically, that means the graph of the hyperbolic sine from the point after x equals 0 would be decreasing. Because we have shown that as x decreases, the value of y will decrease, approaching negative infinity. And for those values of x approaching negative infinity, the graph of the hyperbolic sine would look like this. And this is now the complete graph of the hyperbolic sine of x, defined by e to the x minus e to the minus x all over 2. And you can see that the range of the hyperbolic sine of x is from negative infinity up to positive infinity, or the open interval negative infinity to positive infinity, or simply the range of the hyperbolic sine of x is the set of real numbers. Now, if you draw a line, the line x equals y, or x minus y equals 0, that line will pass through the origin, and the graph of the hyperbolic sine this is the line x equals y, or the linear equation x minus y equals 0. If you transpose y to the left-hand side, you get x minus y equals 0. And this line passes through the origin, and it's a bisector. It bisects the first quadrant and the third quadrant equally. And the graph of the hyperbolic sine is symmetric with respect to this line x equals y, which means that the graph of the hyperbolic sine below is the same as the part of the graph of the hyperbolic sine above the line x equals y. This is the part of the graph of the hyperbolic sine of x below the line x equals y, and above the line x equals y, you have like a mirror image, a similar graph, a similar part of the graph, but above the line x equals y. And we can actually show that the graph of the hyperbolic sine is symmetric with respect to the line x equals y. We first define or give the condition for symmetry with respect to the line x equals y. Symmetry with line x equals y. For y equals f of x, if f of minus x equals negative of f of x, then the graph of the function y equals f of x is symmetric with respect to the line x equals y, or x minus y equals 0. And the function that we want to show is symmetric with respect to this line x equals y is the hyperbolic sine of x defined by e to the x minus e to the minus x all over 2. And from here, from f of x, we find the value of f minus x. And we show that after we simplify, we will get minus negative of f of x. F of minus x is obtained by replacing every x from f of x in f of x equals e to the x minus e to the minus x all over 2. We replace x with minus x, we get f of minus x, and this is equal to this expression when x is replaced with minus x. We get e to the minus x minus e to the negative of negative x. All over 2. The first term is as is e to the minus x. The exponent of the second term simplifies to positive x. Negative times negative is positive x. And the second term is minus e to the power x. Now we factor out negative or minus from each of these terms. This is positive, divided by negative is negative e to the minus x. And this is negative e to the power x, divided by negative, it becomes positive e to the power x. And we write first the positive term, negative e to the x, divided by negative is positive e to the x. And e to the minus x, that's positive, divided by negative is negative e to the minus x. But e to the x minus e to the minus x all over 2 is f of x. E to the x minus e to the minus x all over 2 is equal to f of x. So we have shown that f of x equals negative of f of x. Therefore, we have shown that f of minus x equals negative of f of x. And f of minus x is equal to hyperbolic sine of minus x. We replace x with negative, we replace x with negative. F of minus x equals hyperbolic sine of minus x. And we have shown that the hyperbolic sine of minus x is equal to negative f of x, negative of f of x, where f of x is hyperbolic sine of x. Thus, we have shown that the hyperbolic sine of negative x is equal to negative of the hyperbolic sine of x. Earlier, we have shown that the hyperbolic cosine of minus x is equal to hyperbolic cosine of x. Now we have shown that the hyperbolic sine of minus x is equal to negative of the hyperbolic sine of x. And we therefore conclude that the graph of the hyperbolic sine is symmetric with respect to the line x equals y. That means for this part, taking this part of the graph of the hyperbolic sine, we have a similar part of the hyperbolic sine only on the opposite side of the line x equals y. So to summarize again, the hyperbolic sine of x is defined in terms of the exponential functions e to the x and e to the minus x. In particular, the hyperbolic sine of x is equal to e to the x minus e to the minus x all over 2. And the hyperbolic sine of x is defined for every real number, which means that the domain of the set of the hyperbolic sine of x is the set of real numbers R. And we have shown, based from the graph, that the range of the hyperbolic sine is also the set of real numbers, or the range of the hyperbolic sine is the open interval from negative infinity to positive infinity. And we have also shown that the hyperbolic sine satisfies the property that the hyperbolic sine of minus x is equal to negative of the hyperbolic sine of x. And graphically, that means that the graph of the hyperbolic sine of x is symmetric with respect to the line x equals y, the line that passes through the origin and that bisects the first and the third quadrant. Now we will now define the hyperbolic tangent of x. Similar to the definition of tangent of an angle in plane trigonometry, we define the hyperbolic tangent of x as the ratio of the hyperbolic sine and the hyperbolic cosine. In trigonometry, tangent is equal to tangent of theta is equal to sine theta over cosine theta. And we take this, we call this as one of the ratio properties, ratio identities in trigonometry. That is, the ratio of sine theta and cosine theta is defined or is equal to tangent theta. In hyperbolic function, the hyperbolic tangent of x is equal to the ratio of the hyperbolic sine of x and hyperbolic cosine of x. Hyperbolic tangent of x equals the ratio of hyperbolic sine of x to hyperbolic cosine of x. But we can also define hyperbolic tangent of x in terms of the exponential functions e to the x and e to the minus x by replacing hyperbolic sine of x and hyperbolic cosine of x with their definitions in terms of the exponential functions e to the x and e to the minus x. And hyperbolic sine of x is equal to e to the x minus e to the minus x all over 2. Divide by hyperbolic cosine of x. Hyperbolic cosine of x is defined as e to the x plus e to the minus x all over 2. And this looks like a complex fraction in algebra. And we simplify this complex fraction by multiplying the numerator by the reciprocal of the denominator. And you would see that 2 would cancel out. The numerator is e to the x minus e to the minus x all over 2. We change division by multiplication, and we take the reciprocal of the denominator. The reciprocal of this expression is 2 over e to the x plus e to the minus x. And 2 would cancel out because it's equal to 1. Thus, the hyperbolic tangent of x is e to the x minus e to the minus x all over e to the x plus e to the minus x. And again, we sketch the graph of the hyperbolic tangent of x in the Cartesian plane or the xy plane. First, the domain. What is the set of real numbers for which the hyperbolic tangent of x has a value or is defined? And the domain of the hyperbolic tangent of x, as with the hyperbolic cosine of x and hyperbolic sine of x, is the set of real numbers. That is, for every real number that you would substitute, you may want to substitute for x, there is a corresponding value for hyperbolic tangent of a real number. And the domain, again, of the hyperbolic tangent of x is the set of real numbers. That means you can assign any real number to x and you can calculate the value of hyperbolic tangent of that real number. And we will sketch now the graph of the hyperbolic tangent of x in the xy plane or the Cartesian plane. As with the hyperbolic cosine and hyperbolic sine of x, we assign an initial value to x, which is 0. When x is 0, we find the value of hyperbolic tangent of x using this expression or using this expression, this ratio. The hyperbolic tangent of 0 is equal to hyperbolic sine of 0 all over, which we have calculated earlier, over hyperbolic cosine of 0, which we have also calculated earlier. Or you may find the value of hyperbolic tangent of 0 from here, and it's equal to e raised to 0 minus e to the minus 0 all over e raised to 0 plus e to the minus 0. And we find the hyperbolic tangent of 0 from this expression by replacing every x with 0. And we have e to the 0 is 1. E raised to minus 0 is the same as 1 over e raised to 0. But e raised to 0 is 1. So we have minus 1 over 1 is minus 1. E to the minus 0 is 1, and we have negative in the coefficient of e to the minus 0. So the numerator is 1 minus 1, and the denominator we have e raised to 0 is 1. plus e to the minus 0 is 1 because e to the minus 0 is equal to 1 over e to the 0, but e to the 0 is 1. So the second term simplifies to 1 over 1, which is 1. E to the minus 0 is 1. In the numerator, we have 1 minus 1 is 0. In the denominator, we have 1 plus 1 is 2. And 0 over 2 is 0. Thus, if x is equal to 0, the hyperbolic tangent of 0 or the value of y is 0. And that point, x is 0 and y is 0, corresponds to the origin or the point 0, 0 in the xy plane. This means geometrically that the graph of the hyperbolic tangent of x will pass through the origin or the point 0, 0, like in the graph of the hyperbolic sine. Now we will investigate, as with the first two hyperbolic functions, what happens to the value of the hyperbolic tangent of x if x approaches positive infinity and if x approaches negative infinity. As I said earlier, we now investigate what happens to the value of the hyperbolic tangent of x or the value of y if we let x approach positive infinity. If x approaches positive infinity, that means the values of x are increasing, then y defined as the hyperbolic tangent of x will approach what number? That number is the limit of the hyperbolic tangent of x as x approaches positive infinity. But we have shown that the hyperbolic tangent of x in terms of the exponential functions e to the x and e to the minus x is equal to e to the x minus e to the minus x all over e to the x plus e to the minus x. And we can also use the fact that the hyperbolic tangent of x is equal to the ratio of the hyperbolic sine of x and the hyperbolic cosine of x. And we can also write limit of hyperbolic tangent of x as x approaches positive infinity is equal to, instead of this, you can write limit of hyperbolic sine of x over hyperbolic cosine of x as x approaches positive infinity. And that would be easier to evaluate the limit of the hyperbolic tangent of x. And to evaluate the limit of this ratio, we take the limit of the hyperbolic sine of x as x approaches infinity, positive infinity, over the limit of the hyperbolic cosine of x as x approaches positive infinity. And earlier we have shown that if x approaches positive infinity, the value of the hyperbolic sine of x will also approach positive infinity. This will approach positive infinity, and we have shown this in the graph of the hyperbolic sine of x. As x approaches positive infinity, the graph of the hyperbolic sine is increasing, approaching positive infinity. Similarly, we have shown earlier that as x approaches positive infinity, the value of the hyperbolic cosine of x approaches positive infinity. And this is from the point after x equals 0. So the limit of hyperbolic cosine of x as x approaches positive infinity is positive infinity. But this hyperbolic sine of x is not exactly equal to positive infinity. And the limit of hyperbolic cosine of x as x approaches positive infinity is not exactly equal to positive infinity. Because if you have positive infinity over positive infinity, then that is not equal to 1. And that's what we call indeterminate form. We cannot determine the value of positive infinity over positive infinity. We are only saying that the hyperbolic sine of x is approaching a very large positive real number, and also the hyperbolic cosine of x is approaching a very large positive real number. But if the numerator and the denominator approach a very large real number, if we say very large positive real number divided by a very large positive real number, then the answer would be 1. Hence, the value of the hyperbolic tangent of x as x approaches positive infinity approaches 1. This means that the value of the hyperbolic tangent of x will not be equal to 1, will never be equal to 1, but is only approaching 1. That is, if we assign values of x that are increasing, approaching positive infinity, the value of the hyperbolic the value of the hyperbolic tangent of x or y will approach 1, or y will approach 1. And that line, y equals 1, is a horizontal line parallel with the x-axis and passing through the point 1, y equals 1 in the y-axis or vertical axis. This is the graph of the line y equals 1. It's parallel with the y-axis, perpendicular with this line y equals 1 is parallel with the x-axis, perpendicular with the y-axis, and it's passing through the point y equals 1 in the positive y-axis. Now the graph of the hyperbolic tangent of x as x approaches positive infinity is increasing, and it's approaching y equals 1, but will never be equal to 1. And so the graph of the hyperbolic tangent function of x, if x approaches positive infinity, would look like this. This is part of the graph of the hyperbolic tangent of x. The value of y is increasing but approaching 1 and will never be equal to 1, because 1 is only a limit of the hyperbolic tangent, the value of the hyperbolic tangent of x as x approaches infinity. And this line y equals 1 is what we call a horizontal asymptote of the graph of the hyperbolic tangent of x. asymptote means that the graph of the hyperbolic tangent of x is approaching the line y, this horizontal asymptote, with equation y equals 1. But they will never intersect. The graph of the hyperbolic tangent of x and the line y equals 1 will never intersect, because the hyperbolic tangent of x will never be equal to 1, because 1 is only the limit, a number to which the value of the hyperbolic tangent of x approaches. Now we investigate what happens to the value of the hyperbolic tangent of x if we now let the values of x approach negative infinity, or if we let x to continuously decrease. If we let the values of x to decrease approaching negative infinity, then y, the value of y equal to hyperbolic tangent of x, will approach what number? That number is the limit of the hyperbolic tangent of x as x approaches negative infinity, and we find that limit. In terms of using the definition of the hyperbolic tangent of x in terms of the exponential functions e to the x and e to the minus x, the limit of the hyperbolic tangent of x as x approaches negative infinity is equal to limit of e to the x minus e to the minus x over e to the x plus e to the minus x as x approaches negative infinity. But another way to find the limit of hyperbolic tangent of x as x approaches negative infinity is to use the fact that hyperbolic tangent of x is equal to hyperbolic sine of x over hyperbolic cosine of x. So using that ratio, the limit of hyperbolic tangent of x as x approaches negative infinity is equal to the limit as x approaches negative infinity of hyperbolic sine of x over hyperbolic cosine of x. And using one of the properties of limits, the limit of this ratio is equal to limit of hyperbolic sine of x as x approaches negative infinity over the limit of hyperbolic cosine of x as x approaches negative infinity. As we have shown earlier, the limit of the hyperbolic sine of x if x approaches negative infinity is negative infinity. The value of the hyperbolic sine of x is not exactly equal to negative infinity, but is approaching a very, very small negative real number, denoted by negative infinity if x approaches negative infinity. And we have also shown earlier that the limit of hyperbolic cosine of x as x approaches negative infinity is positive infinity. Again, the value of the hyperbolic cosine of x is not exactly equal to positive infinity, because in the first place, positive infinity is not a real number, but it's only a notation used to denote a very, very large positive real number. So the limit of the value of hyperbolic cosine of x is approaching a very, very large positive real number if the values of x approach a negative infinity. But if you have this limit negative infinity and this limit positive infinity, a very, very small real number divided by a very, very large positive real number is equal to 1. They may be numerically the same but opposite in sign, and so the ratio, their quotient, is negative 1. This means that the value of the hyperbolic tangent of x, or the value of y equals the hyperbolic tangent of x, will approach negative 1 if we let x approaches negative infinity. If x approaches negative infinity from a point after 0, if you take values of x approaching negative infinity, the value of y will approach, the value of y is decreasing, will approach negative 1, or it will approach y equals negative 1. Geometrically, that means that the graph of the hyperbolic function of x, the hyperbolic tangent of x, the graph of the hyperbolic tangent of x from the point x equals 0 will be decreasing, and as x decreases, the value of the hyperbolic tangent of x will approach negative 1. And the graph of the hyperbolic tangent of x will approach the line y equals negative 1. And this line y equals negative 1 again is a horizontal line parallel with the x-axis, perpendicular with the y-axis, and will pass through a point on the y-axis at y equals negative 1. This is the graph of the line y equals negative 1. It's parallel with the x-axis, perpendicular with the y-axis. And the graph of the hyperbolic tangent of x from the point after x equals 0 will be decreasing if you assign values of x that are decreasing. And the value of the hyperbolic tangent is decreasing and will approach this line y equals negative 1, but never touching the line y equals negative 1, because the value of the hyperbolic tangent of x will never be equal to negative 1, or it's not exactly equal to negative 1, because negative 1 is only a limit of the hyperbolic tangent of x if x approaches negative infinity. Hence, the line y equals negative 1 is also a horizontal asymptote for the graph of the hyperbolic tangent function of x. Asymptote means that the graph of the hyperbolic tangent of x is approaching the line y equals negative 1, but will never intersect the line y equals negative 1, because this line y equals negative 1 is a horizontal asymptote, which means that the value of y equals negative 1 is not a value of the hyperbolic tangent of x, but a limit of the hyperbolic tangent of x if x approaches negative infinity. And this is the complete graph of the hyperbolic tangent of x. And from this graph, you can tell the range of the values of the hyperbolic tangent of x. That means the values of y equal to the values of the hyperbolic tangent of x. and the range is from -1 to +1, but excluding -1 and +1, which means that the range of the hyperbolic tangent of x is the open interval from -1 to +1. For your assignment, please try to show that the hyperbolic tangent of -x is equal to negative of the hyperbolic tangent of x. Earlier, we have shown that the hyperbolic sine of the hyperbolic sine of negative x is equal to negative times the hyperbolic sine of x. In here, you will now show that the hyperbolic tangent of -x is equal to negative of the hyperbolic tangent of x. And to do that, to show that, you use the definition of the hyperbolic tangent of x in terms of the exponential functions e to the x and e to the minus x. And that completes our lesson for today. We will continue with identities involving the first three hyperbolic functions, the hyperbolic cosine of x, hyperbolic sine of x, and hyperbolic tangent of x. If you have questions about the lesson today, please ask your questions in the comments below. Thank you for joining me in my class day in calculus.